Now we will look at an example, molar specific heat of hydrogen gas. Examining the molar specific heat of hydrogen as a function of temperature, we see that the vibration does not contribute to the molar specific heat at room temperature. Explain why, modeling the hydrogen molecule as a simple harmonic oscillator, the effective spring constant for the bond of the hydrogen molecule is 573 newtons per meter. So here is the hydrogen molecule, the two atoms with masses m1 and m2, which are the same. Now in this case we have no external force acting on this system. We have a fixed center of mass and we can define the velocity of m1, u1 with respect to the center of mass and velocity of m2, u2 with respect to the center of mass. So this is approaching the center of mass. This is basically going away from the center of mass. And this no external force tells us that the linear momentum is conserved, which is basically saying m1u1 plus m2u2, and I'm considering the motion on the x-axis here, is equal to 0, and we have a fixed center of mass. So this implies that the change in the linear momentum x components should be 0 because we have no external forces. So this allows us to write the second mass velocity in terms of the first one minus m1 u1 divided by m2. Well, this is one-dimensional, so no need to include the vector sign here. It's just the signs of these numbers tell me the direction. So if I write the velocity of m2 now with respect to m1, so let's do that. Velocity of m2 with respect to m1, it would be u is equal to u2 minus u1. Right, so we can substitute for u2 minus m1 u1 divided by m2, and then we have minus u1 here. So we can write this in u1 parentheses minus u1, 1 plus m1 over m2. And you can see that u1 can be written in terms of u as minus u, 1 plus m1 over m2 to the power minus 1. So if I define an effective mass, mu effective, which is equal to m1 m2 divided by m1 plus m2, and I call this mu, and 1 over mu is equal to 1 over m1 plus 1 over m2, you can see that u1 can be written as minus u times m2 over m1 plus m2, which is the effective mass divided by m1. So it is minus u mu divided by m1. Okay, so now I'm going to write the total kinetic energy of the system. If I write the total kinetic energy, 1/2 m1 u1 squared plus 1/2 m2 u2 squared, I see that this is 1/2 m1. For u1 I substitute minus u mu over m1, so it's going to be equal to u square mu square over m1 square, and then I have plus 1 over 2 m2 u2 square, which is m1 over m2 square u1 square. So it's going to be m1 square over m2 square multiplied by u1 square, but u1 is minus u mu over m1. So it's, for u1 I substitute minus u mu over m1. So it is u squared mu squared over m1 squared. Now let's see what's happening here. M1's cancel, and I have m1 squares canceling here, and m2 cancels this m2. So I find that this is this can be written as 1 over 2 mu square u square parentheses 1 over m1 plus 1 over m2. But 1 over m1 plus 1 over m2 is 1 over mu, so this is nothing but 1 over 2 mu u squared. So this tells me that the kinetic energy of this system, considering the center of mass reference frame, can be written in terms of the an effective mass, mu effective, that is attached to this spring. So its kinetic energy, the total kinetic energy, is just equivalent to that of a single mass that would be attached to this spring. So if I write the translational kinetic energy, it has three components: 1 over 2 mu ux squared plus 1 over 2 mu uy squared plus 1 over 2 mu uz squared. So by defining the velocity of m2 with respect to m1, I have fixed m1, and then I'm considering the relative velocity u of m2 with respect to m1, and that is the relative velocity that is entering this effective mass interpretation. So this, according to equipartition theorem, gives me 3 over 2 Boltzmann constant times temperature to the average energy of the system. Then we have rotational kinetic energy, which is 1 over 2 Iy, moment of inertia for rotations about y-axis omega square, plus 1 over 2 Iz omega square. There is no Ix because Ix is 0. Remember that moment of inertia is Ix, which is integral r squared dm from the x-axis, is equal to 0 because r is equal to 0 with respect to the x-axis. So this gives me a contribution of Boltzmann constant times temperature according to equipartition theorem, and the vibrational kinetic energy 1/2 kx squared for this effective mass plus 1/2 mu v squared gives me a contribution Boltzmann constant times temperature to the average energy of the system. Now the spacing between the energy levels is h bar omega, as we have seen in the quantum harmonic oscillator. So we have h bar square root k over mu. And at this point, I note that M1, what I called M1 and M2, are the same thing. M, it's the mass of the hydrogen atom, so that mu is equal to M1 squared divided by, or M squared divided by 2M, which is half of the mass of a hydrogen atom, M over 2. All right. So with that, I can see the spacing between the energy levels, delta E, is h bar square root 2k over m, square root 2k over m, when I substitute for the effective mass m over 2. And if I calculate what this number is, the spacing between the energy levels, delta E, that is Planck's constant 6.626 times 10 to minus 34 joule seconds divided by 2 pi, reduced Planck's constant. Then I have 2 times k, the spring constant. So this is Boltzmann constant. So let's not confuse this k with the spring constant k. All right. And here I have twice the spring constant, 573 newtons per meter. The mass of hydrogen, 1.67 10 to minus 27 kilograms. And then I take the square root. That's the mass of a proton. 8.74 10 to minus 20 joules. So at this point, I can ask myself, at what temperature is the translational kinetic energy comparable to this delta H? So 3 over 2 kBT is equal to 8.74 times 10 to minus 20. This gives me a temperature of 2 over 3 8.74 times 10 to minus 20 divided by 1.38 Boltzmann constant, 10 to minus 23. This gives me a temperature of 4220 Kelvin. All right. So therefore, we see that the vibrational excitation of the vibrational modes are completed when I have a temperature even higher than this temperature, 4220 Kelvin. The contribution from the vibrational part will be basically effective. Okay, so we looked at the molar specific heat of hydrogen gas. Examining the molar specific heat of hydrogen, we see that vibration does not contribute to the molar specific heat at room temperature. So we can explain this by looking at hydrogen molecule as a simple harmonic oscillator, and the effective spring constant is 573 newtons per meter. Now, when I look at the hydrogen molecule, I can analyze this from the fixed center of mass point of view, because I have no external forces acting on the system. The linear momentum is conserved. I can write the velocity of the second atom with respect to the first one. It is minus m1 u1 over m2, and the relative velocity is u2 minus u1. So it's the velocity of m2 with respect to the center of mass minus that of m1. By doing so, I find that if I define an effective mass, 1 over mu equals 1 over m1 plus 1 over m2, and writing the total kinetic energy of these two atoms, I see that it's in the form 1/2 mu u square, where u is the relative velocity of m2 with respect to m1. So we fixed m1, and then we can replace this whole system with an effective mass mu attached to a spring with spring constant k. The translational kinetic energy, 1/2 mu ux square plus uy square plus uz square, gives us 3/2 kt contribution using equipartition theorem to the energy of the system. The rotational kinetic energy contribution is kT, because we don't have Ix contribution. It is 1/2 Iy omega square plus 1/2 Iz omega square. Vibrational kinetic energy is 1/2 Kx square plus 1/2 mu v square. That is kBt. So delta E to excite the vibrational mode, h bar omega, is basically h bar square root 2k over m. It corresponds to 8.74 10 to minus 20 joules. So what is the thermal energy at room temperature? So if you calculate the thermal energy at room temperature, kBTR, that would be equal to 1.38 times 10 to minus 23 times 300 Kelvin, or you can calculate this using the KBT value at room temperature is 1 over 40 electron volts, which is 1.6 10 to minus 19 divided by 40. So you can see that this number will be less than the spacing between the energy levels. Therefore, at room temperature, we can see that vibrational modes are not yet excited. So we see no contribution from vibrations of the atoms to the molar specific heat because the vibrational modes at room temperature are not yet excited. So how did I determine? Because the energy levels of the quantum harmonic oscillator are given by n plus 1/2 h bar omega, n plus 1/2 h bar omega, corresponding to energy spacing of h bar omega. So I calculated h bar omega as h bar square root k over mu, and substituting the numbers, I see 8.74 10 to minus 20 joules, and I see that the room temperature thermal energy, KTR, is basically 1.6 10 to minus 19 divided by 40. So if you take this to be 2 divided by 40, let's say, it is roughly equal to 1 over 20, which is 0.05 times 10 to minus 19 joules. So you can see that this energy is not enough to excite vibrational modes. Now, at what temperature is the translational kinetic energy comparable to h bar omega? For example, we can look at this value 3/2 kT. Now I can see that that temperature is 4220 Kelvin. So I should be in the range of thousands of Kelvin in order to see excitations to higher excited states for the vibrational modes of the system.